We'll now turn to Module 4 and perform some probability calculations with this log normal distribution of stock prices. And it's it's going to be these probability calculations which give us some additional insight in the derivation of the Black-Scholes formulas. So, first of all, we know that the log of the ratio of ST and S0 is normally distributed. That's just simply our model, and it's the definition of log normally distributed S. Another way of saying it is that we're making the assumption that the return from time 0 to time t is in fact normally distributed with the parameters we see here in the normal notation. So we can, from this statement, at least express formulaically what's the probability that the stock price at time t is less than k. Now, of course, k, you may recall, is the symbol, the notation that we have tended to use for a strike price in a put or a call. So that's the background of these calculations, is we're thinking about, well, what are the probabilities that S is less than K, which is important for puts, and we'll see in a moment what's the probability that S is bigger than K, and that's important for calls. Now, we're working in the real-world model here. We have alphas, not R's. So, but for this model with alpha, we can calculate or express what's the probability that ST is less than K. Well, how does one do this? Well, what we want to do is convert ST into a unit normal. And how would we do that? Well, we have it here. We divide ST by S0, both sides, and you're familiar with this calculation, but you may recall that instead of ST less than K, we might say ST less than divided by S0 is less than K divided by S0. I could then take a log of both sides. And now I know that this log, the probability I seek, is the probability that a normal variable is less than the log of K over S0. So now I can subtract the mean of the normal, divide by the standard deviation, and that's where this expression here goes. I end up with a unit normal by taking the normal, which is the log of ST over S0, subtracting the mean, dividing by the standard deviation. And this is, in fact, the definition very similar. You'll notice the notation D2 comes from the Black-Scholes formula. And the reason we have a caret or a hat on D2 is to note that this D2 is identical to the Black-Scholes D2, except it's a real-world D2. We're using alphas here, not R's. So that's important, but the definition of D2 would be minus this expression. If I took this expression here and I multiplied it by -1, I would get the Black-Scholes formula D2. Multiply this expression by -1, I'd get the Black-Scholes formula for D2, but again, we have to put a hat on it because it is the Black-Scholes formula for D2 where we're using an alpha instead of an R. And using exactly the same derivation, we would find that the probability that S was bigger than K, and again, in both cases, we should, for definitional purposes, perhaps put an equals, but again, we have continuous distributions here. The probability that S is bigger than K is N of positive D2, again with a hat because we're using alpha. This is important because you will recall, and we're going to get to that in just a few slides, that in the Black-Scholes formula for a put, we had an N of minus D2. And for the Black-Scholes formula for a call, we had an N of positive D2. So the Black-Scholes formula, even here, where we go from alphas to R's, and that's why we get rid of the little hats on the D's, we see right away that those D's, the D2s, both represent probabilities of S being bigger than K or less than K, which are important for calls when S is big and puts when S is small. So when the current stock price is S0, in the real world where we're using alpha, the probability that a call option will be in the money, that's the probability that S is bigger than K at expiry, is equal to N of D2. And the probability that a put is in the money in the real world is equal to N of minus D2. These are real-world probabilities. So if you bought a call, this would be the real-world probability of getting a payoff. And if you bought a put, this is the real world, the probability we think about as truly reflecting our odds of getting a payment. We would have the probability of minus N of minus D2. So this would be a call or a put. In order to price these options, we don't want to assume these real-world probabilities, because then we would need to use a real-world discount rate, which is denoted gamma in earlier chapters. Instead, we price the option assuming risk-neutral probabilities and R instead of alpha, and then we can use the risk-free rate to discount our prices.